Thank you everyone for coming and following along the Colombian kind of vibe. I'm also from Colombia, so Daniel Kahneman and Amos Tversky showed us how hard it is to think statistically. People have biases and misconceptions about the way to think intuitively about stats. In fact, even very experienced researchers who have studied statistics for a very long time, they are prone to biases and misconceptions when they think intuitively about stats. So for example, if I told you disease A kills 1,200 out of every 10,000 people versus disease B that kills 20 out of 100, you're more likely to think that disease A is more dangerous. So thinking statistically is very hard for us. We have very poor statistical intuition. At the same time, we're having a reproducibility crisis in science. Reports are showing that scientists cannot copy each other's results. And one of the main reasons for this crisis is poor statistical understanding and lack of transparency in the presentation of the methods. So for example, here, 29 research groups were given the same data to analyze. And you can see that every bar is a research group. Every group found a different result. They had different methods for analyzing the same data. So the takeaway message is clear. Methods matter. And most scientists agree that some of the most important solutions for this crisis is a better understanding of statistics and a more transparency of the results of presenting the methods. So why am I talking about programming? Because programming is the tool that is going to allow us to have the greater transparency, because it's easier to share code than to share analysis on Excel. But before we start sharing code, we need to learn how to code. Most graduate students start their PhD with no knowledge of programming and at most one basic stats course. But wouldn't it be better if we started earlier? So the solution then would be to teach our undergraduate students statistics and programming at the same time. But teaching a very hard, not intuitive subject with a very hard subject like programming, it's very hard. And most biostatistics professors are trying to figure out, well, what is the best method that we can teach these two very hard subjects to our undergraduate students without overloading them? So can we do better? I think we can. So for my public scholars project, I'm going to be using learning theory coupled with statistics and programming to inform our teaching of programming and statistics, and hopefully improve the learning outcomes of our students. So how am I actually going to do this? I'm developing some laboratory manuals that will be introduced in biostatistics courses. These lab manuals will introduce programming concepts into classes. A very large Intro to Stats course, which has hundreds of students, and a very much smaller advanced statistics course. And this will let us see if this same method is useful for both types of settings. I'm going to be using surveys and looking at the students' grades to assess the success of these labs. And so the surveys will help us see if the students are feeling better and what's the perceived difficulty of the labs. And then the grades will help us make sure that their statistical understanding is still increasing. So why am I talking about learning theories? Learning theories tell us that there's a limit to the working memory that people have. That means that there's a limit to the amount of information that we can give people, and therefore the way that information is presented, connected, and practiced matters for learning outcomes. And so what does this mean in terms of the current labs? It means that if you have some programming that it's not very well explained, that has lots of wordy explanations, students are going to have a very hard time putting the two pieces of information together. It's better if we give them the information consolidated in a better type of diagram. It also means that if I give you an open-ended question and hope that one day you'll find a way to solve this problem, that's not the most effective way. Instead, I should show you how to solve that problem and tell you why, and ask you to think why we're solving the problems that way, and over time, give you more opportunities to practice it. It also means that if there's any extra information that it's not relevant for that current concept, that's going to hinder your learning. And so there's no point in teaching all the programming concepts at the same time, but they should be coupled with the statistical concepts that they're relevant to. It also means that very complex information shouldn't all be taught together. Instead, I should teach you all the different concepts in an isolated fashion and then show you how to integrate them in such a way that you can see a whole picture by the end, but you learned just bit by bit. And so with this, I'm hoping to see that our students are learning faster, with less anxiety, and being less overwhelmed. And hopefully they'll be able to transfer that programming into their future. And so, since this is a very non-standard project for a zoology student, the Public Scholar Initiative is giving me the opportunity to include these lab manuals and these research into my dissertation. And so, overall, I hope that my public contribution will be twofold. First, it'll help train our new generation of scientists to learn to code and how to share code, so we kind of help this reproducibility crisis. But I'm also hoping that the job outcomes of our undergrads will be improved, since coding is the skill of the future. Thank you.